Good afternoon, everyone. Hopefully everyone can hear me. Okay, all right, yeah. Could someone just confirm that y'all can hear me clearly? All right, wonderful, thank you. Yeah, so get started in a few minutes. Hi, Mihee, can you hear me?
Yes, I can hear you. Hi, Professor.
Right, okay. So yeah, if you want, you can share your screen, right? So you can share your slides.
Okay. Can you see the screen?
Yes, perfect. Okay, so yeah, let's give people a few minutes to join, and we can get started maybe in 2 or 3 minutes.
Okay.
Right, thank you. All right. So I think critical number of us are here. So good afternoon, everyone. Hopefully everyone's doing well. Yeah, once again, thanks for your flexibility in today's virtual class. So yeah, Mihee, please get started. So the lecture is being recorded, okay, just for your reference, and I will be posting a video of the lecture recording on our Discord. So okay, all right. So Mihee, you can take over.
Yeah, sure. Thank you. Hi all. My name is Mihee, and I'm pursuing my PhD under Professor Vladimir Pavlovich. Today, I'm going to present my work on trajectory prediction that I am doing with Professor Kapadia, and especially the trajectory prediction, understanding the uncertainty derived from social and environmental interaction. So what are the trajectory prediction instances found in the real world, and why are they important? Let's find out why predicting the future behavior of moving agents is important problem in some real world examples. In the setting of this autonomous driving on a public road, it is essential to have an accurate understanding of where the other vehicles and pedestrians will likely be in the future for safe and effective action planning while avoiding collisions with other vehicles or pedestrians. And another example we can think of is the escaping scenario in an emergency. In this example, people should be able to recognize where the exit is, that is the environment, to get out of the room in this maze-like environment. To solve these problems, we first need to think about what makes this behavior planning in the future so difficult. Let's think about it on this self-driving scenario example. The primary thing is the inherent problem that we never know whose destination is where. In this example, the first blue steps are observed, and we want to predict the next step, but only based on the given blue steps. We cannot determine for sure where this vehicle is going to head. It may go to the right side of the proceeding direction this way, or to the left of the proceeding direction this way, or just keep its moving direction this way. So if we know where the goal position of the agent is heading, the rest of the future steps follow it. But the problem is we never know where the exact goal position is, which arouses the uncertainty. And secondly, another thing to be considered for the solid prediction is that the agent must be able to recognize the navigable space. Otherwise, the vehicle might move out of the roads like this way, which makes an accident. And also, the other agent's movement is important factor to decide the target agent's future behavior. In this example, we can see the two vehicles with different color, red and cyan colors. The dashed line here is the ground truth trajectories, past trajectories, the 4 steps, and the rest of the future step, ground truth. And the dotted line to this direction are the predicted future steps. As well as these predicted future steps are deviated from the ground truth future steps, more severe problem is that the two agents' prediction collide in the middle of the movements, right? Like this, at this point. It is very unrealistic, so it is essential to understand where the other vehicles or pedestrians will likely be in the future for safe and effective action planning. Now, let's formulate the problem to model these vectors. Given a sequence of past trajectories of an agent, such as pedestrian, vehicle, or cyclist in some fixed past time step, we like to predict the future trajectories of these agents up to some future time step. At this example, the past trajectories, these blue points, are given in this direction. So this is the last observed step. Though this agent can move to any direction from this last observed step, like this, or like this. Considering this past movement direction, it seems the most reasonable future movement is like this, just going straight, right? But as seen in the previous slides, the agent's movement is greatly influenced by environmental information. So not only the very basic conditions for solving the problem, but also additional context should be considered, such as the scene environment. If the nearby environment of this agent is like this, these predicted future behaviors obviously violate this environmental condition, and it is unrealistic. So under this environmental condition, most reasonably diverse predictions that we can expect would be these three cases. As we can see in this example, the environmental condition is essential factors because it can provide realistic predictions without collisions, as well as it can reduce the uncertainty that comes from the intrinsic problem of not knowing where the goal position is. Another context is the neighbor agent's trajectories in the same time step. In the previous slide, we already saw how it is important to be able to recognize the neighbor agent to avoid collisions with that neighbor agent. Now, let's organize these conditions to compose the modeling factor. First, the primary problem to solve is to cover the uncertainty, which is heavily dependent on the goal position. Once the goal positions are well predicted, the rest of the future steps can be predicted as a consequence following the goal position. And then we need to achieve a collision-free model from the environmental obstacles and neighbor agents. There are prior works that study the trajectory forecasting problem considering these modeling factors. Trajectron++, agent Fover, most of them use the map encoding to learn the environment and neighbor encoding to learn the context of neighbor agents. They use the one-dimensional encoded feature to obtain the collision-free model from the environmental obstacle and neighbor agents. However, they overlooked the goal position is the key element for overall prediction diversity. YNets, on the other hand, they first predict the goal positions using the environment information in order to narrow the uncertainty of the future behavior based on the environment information. However, they did not consider the neighbor of the target agents, which may cause the collisions between agents. So we propose our model MuseVA by incorporating all of these factors in order to achieve both realistic that avoids collisions and accurate future predictions of the trajectory without collisions with both environmental obstacles and neighbor agents. The full name of the proposed model is MuseVA, Multi-Scale VA for Environment-Aware Long-Term Trajectory Prediction, and it was accepted in CVPR 2022. Let me explain the overview of our MuseVA by introducing how each of the modeling factors are explained in our model. I'm just giving an overview here, and more detailed explanation will follow in the later slides. First, to resolve the intrinsic uncertainty of the future behavior, we leverage conditional variational autoencoder, conditional VA, as our backbone framework. VA provides a probabilistic model, not just one deterministic output. So this VA-based, this VA backbone model can give us the prediction of the future, can give us the distribution of the future trajectory, and we can get multiple different predictions by sampling from the obtained distribution. Here, we especially use the conditional VA, so conditioned on the input of the past observed trajectories, it outputs the future trajectory distribution. And based on the conditional VA backbone, we divide the prediction flow of our model into two stages, macro and micro stage. And the first stage, macro stage, the model predicts diverse goal positions. The motivation is that the goal position reveals the intention of the target agent's overall movement. Once the goal predictions can be obtained reasonably diversely, detailed future forecasts are naturally obtained accordingly. And we aim to have SYN-compliant goal predictions. So we represent trajectories as a heat map, and this heat map image is aligned with the environment map image. This strategy allows the goal position prediction to be achieved in a SYN-comparable manner that avoids collisions with the environmental obstacles. Next, we move on to the micro stage. Here we predict all the fine-grained future steps in world coordinate using the goal prediction obtained from the macro stage. Unlike the pixel-based learning in macro stage with heat map representation, in this stage utilizes recurrent neural network in world coordinate to reflect the sequential properties of set of trajectories. Also, while predicting each step, the model tries to avoid collisions with neighboring agents by learning the interaction between the other agents and the target agents. So this is the overview of Muse VA, and now let's see how each stage is elaborated. Before diving into the macro stage, let's clarify some definitions and terminologies we use in our model. Now we know our goal is to predict the future trajectories given the past trajectories. We will represent the past trajectory with X and future trajectory with Y. And here I denotes the agents and T denotes the time duration. So here, and here we assume TP as the past time duration and TF as the future time duration. So here this set of XIT represent the past trajectories of agent I during the past time duration TP. Typically in the prior works of trajectory forecasting problem, 4 or 8 observed steps are given as the past trajectories and 12 future steps are predicted. In the previous slides, I introduced the macro stage as the stage to predict the goal positions of an agent. Actually, we define and use two types of goal position in our model, long-term goal and short-term goal. First, the long-term goal means the final step of the future trajectories. So it is the trajectory at time step T plus F in this example figure. The blue points are the observed past trajectories, and the others are all future steps. Here, this last step becomes the long-term goal. And we use the notion of short-term goal, or in other words, waypoints. It is the intermediate steps of the future trajectory. So it can be located in between TP and TP plus F. In this example, we are assuming only one short-term goal here, and it is the middle point here. But also, we can assume two short-term goals like this. Then these two short-term goals are defined at 4th and 8th places of the future steps like this, with an equal distance from each other between the last observed step and the last future steps. And of course, we can have 3, 4, or 6 short-term goals as long as it can keep the equal distance between the goal positions. So in the macro stage, we will predict these long-term goal and short-term goals. And especially in our experiments, in our models experiments, we use 2 short-term goals. So in summary, let me explain this overview again. The macro stage predicts the course predictions, the goal positions. First, in long-term goal CVA model, the long-term goal is predicted based on the CVA framework. And then in the short-term goal net, given the long-term goal, the waypoints, the short-term goals will be predicted. After that, in micro stage, in the world coordinate, or the fine-grained trajectory, future trajectory will be predicted. For your understanding, I mark these sequential prediction stages in the upper right corner here so that you can refer to it whenever you are lost. And this slide introduces the first macro stage, long-term goal CVA. The goal of this stage is to get the SYN-compliant long-term goal prediction. So to perfectly align the trajectory with the SYN map, the trajectories are represented with a heat map in this stage. Let's first check how the SYN map is given. Basically, it is the semantic segmentation map. And in this example, it is this binary map where white space represents the navigable space and the black space is non-navigable space, such as words. In this maze-like space, the agent is moving here. And this is the enlarged view of the region of the interest near the trajectory. The blue points are the past trajectories, and the red points are the future trajectories. Here we can see the SYN information we need for the prediction of this trajectory is not the whole SYN, right? But only this local view nearby the target agent's trajectories are enough. So in our model, we use the semantic segmentation of the SYN map in the local view, and the local map is created in a way to be centered at the last observed step. Now let's see how the input and output look like in CVA model. The input is the SYN map as defined above, the local semantic map, and the corresponding heat map of all past trajectories, like this. So these 8 past trajectories are represented with this cyan color, and it will have the value close to 1, and all other pixel values will be 0 as the background. Yeah, and here we denote the local view of the semantic map as IM, and the heat map of all past trajectory as IX, image of X past trajectories. And these two images are concatenated in tenor dimension, like this, aligned, and then fed to the long-term goal CVA. Then the output of the final step of the future trajectory, the long-term goal, is predicted. Also, the output is also obtained in the form of a heat map and represented as image of long-term goal. You can see this long-term goal in heat map is matched with this last position of the future trajectories. If we see all of these inputs and output in an aligned way, it looks like this. So we can expect that the prediction, long-term goal prediction, can be obtained in a way that avoids collisions with environmental obstacles. This is overall architecture of long-term goal CVA model. The joint pixel-based environment trajectory input IM and IX, this input, is encoded using UNet architecture backbone, which shows excellent performance on semantic segmentation learning. And as aforementioned, conditional VAE is used to predict the future trajectory distribution conditioned on the past trajectory information. You can see here that during the training, both the input, image of the semantic map and image of the past trajectories, and the output, the ground truth long-term goal heat maps are given during training. The red line is during training. But in test time, only the past trajectories are fed to the fed to predict the long-term goal heat map. This blue line is only in inference. So in test time, conditioned on the past information, we predict the future. And so the conditional prior latent distribution P is learned based on the past trajectory, and the posterior latent distribution Q is learned based on the future trajectory during training. These prior distribution and posterior distribution gets closed by the KL divergence loss during training here. KL divergence loss between Q and P. As a result, in inference time, only with the conditional prior distribution from the past trajectory X with Px, we can provide reasonable prediction Y. Yeah. Also, for the first term of the conditional VA loss, which is the reconstruction loss, we compare the predicted long-term goal heat map with the heat map created based on the ground truth long-term goal. The benefit of conditional VA is that we can cover the uncertainty by creating multiple predictions. Once the latent distribution is learned based on the past trajectories, then we can sample multiple different latent factor W from this distribution. And by feeding this W to the decoder, we can generate multiple different long-term goal prediction. So we can cover the uncertainty. The second macro stage is short-term goal net. One more image coordinate-based short-term goal predictions are made here in our model because we want to have rough idea of all future trajectories that are well aligned with the environment. But unlike the long-term goal CVA, this short-term goal net stage outputs the one deterministic prediction based on the long-term goal from the long-term goal CVA. This is because the diversities of the future behavior is already covered from the long-term goal CVA, the previous model, while predicting the long-term goal. So let's check the input-output format of the short-term goal net. Short-term goal net has the same input as the long-term goal CVA, except that it has one more input, a heat map for long-term goal position. And the output is the series of heat maps, each of which represent each short-term goal and long-term goal. In the previous slide, we checked that the inputs and output of the long-term goal CVA is like this. Now in short-term goal net, all of them is used as input, the past trajectory heat map and the semantic map and these long-term goal predictions, all of them used as the input of the short-term goal net. And then the output is the two short-term goals, first short-term goal, second short-term goal, and one long-term goal. Short-term goal net regenerate this long-term goal for the seamless trajectory flow from the short-term goals to the long-term goal. So this long-term goal prediction in short-term goal net is almost the same as the long-term goal prediction from the long-term goal CVA, but more well aligned with the short-term goal predictions in short-term goal net. This is the architecture of the short-term goal net. Again, our input in short-term goal net is the ground truth long-term goal during training, this red line, and the predicted long-term goal during inference, the blue line, in addition to the local semantic map IM and past trajectory heat map IX. These three inputs are given. And we use UNet one more time here for effective segmentation learning. And the output is the two short-term goal heat maps and one long-term goal heat map, three heat maps. These predicted heat maps are then compared with the heat maps of ground truth, short-term goals, and long-term goal. So the short-term goal net loss is simply reconstruction loss. Now we have finally reached our final stage, the micro stage. Here we predict complete future trajectories in world coordinate. So no more heat map representations of the trajectories. We leverage conditional VA in this step again. In this micro-stage architecture, the sequence of full past trajectory X and future trajectories Y are processed with LSTM, which is effective to learn the sequential information. The conditional prior distribution is learned based on the past trajectories, and posterior distribution is learned based on both past and future trajectories. In addition to the latent factor G from this latent distribution, as the input of the decoder, we feed the LSTM feature of the predicted short-term goal and long-term goals from the macro stage. This course prediction information helps the granular prediction in micro stage to be obtained in a way that avoids environmental obstacles. Then the decoder outputs the complete future trajectories based on the recurrent neural network, and the predictions are compared to the ground truth future trajectories, which gives the reconstruction loss here. So we almost came to the end, but what is the last remaining modeling factor we should consider? There is one more thing. The last factor is the context of neighboring agents to avoid collisions between agents. The prediction should be generated in reflecting the agent-to-agent interaction. So we adopt the strategy from the prior work color scan. This paper introduces two strategies to learn the interaction between agents, pooling and colors, the collision loss. First, the pooling strategy is to learn all the decoder features of neighbor agents together with the target agents at each future time step. In this figure, we assume there are 3 agents in the same scene and time duration. That is, they are all neighbors. Let's say the target agent is this blue one, and its neighbors are gray and red agents. The batch of these 3 agents encoded feature is fed to the GRU decoder, this decoder. And then these GRU features are max poored so that the blue target agents can learn its social context with gray and red neighbors. Reflecting this social context, the future step is predicted, and this process repeated until all the future steps obtained again and again. In addition to the pooling, to explicitly penalize those confliction cases, co-loss is suggested in this paper. The exact loss is as described here, but let's just focus on this Dij minus gamma collision part. Dijt denotes the distance between ith and jth agents at future time t. So I and j, these agents are neighbors. And gamma collision is the hyperparameter we set. It is a threshold to determine the collisions. So for example, if gamma is 0.5 meter, whenever the distance between the agent Dij is smaller than 0.5 meter, it is penalized because it is considered as the collision case. So the more collisions and the smaller the distance between agents, the greater the loss. So we considered all of the modeling factors of Muse VA. We have looked at every part of the Muse VA. And this paper is uploaded in the archive, so you can check more details in the paper. But still, do you have any questions before we move on to the experimental results?
So yeah, I would encourage everyone to think carefully about what Mihee has presented so far. Perhaps compare it to the presentation that Sam gave last week, where he talked about transformer architectures, right, which are also sequential prediction models, and perhaps understand the relationship between those two. So Mihee, maybe a quick question for you then. So yeah, you've presented this extremely a complicated multi-stage architecture, right, for trajectory prediction. So my question for you as a retrospective, right, is if you were to revisit any of these design decisions, right, what are some of the components which you believe you might want to change? And of course, this, like after you describe your evaluation, you will give us some ideas. But I just wanted to, ask you a high-level question about the design decisions that you made at the time of this project, and now that you had some time to think about it, right? What might you do differently?
Mm. Yeah. Thank you for the question. That's a tricky question. Actually, I know what's the disadvantage of my model, but I don't know how to change it exactly. The disadvantage is that, as you mentioned, this is very multi-stage learning. So it takes lots of time to learn each of 3 models, though they are able to be run in parallel. So we can train each of 3 models at the same time and collect the final results at the end of the training. But still, we have to train 3 models, and especially the macro stage, which use the image inputs, the heat map trajectories and semantic map. It takes really, really long time to finish the training. Yeah, but I don't know how to improve that part yet.
Okay, thank you very much, and we can discuss more after you present the results.
Yeah.
No, but it's a very interesting note, and also for the class, right? So you mentioned that the macro stage, right, which essentially uses image-based representations, takes longer to train than the micro stage, right, which are essentially sequential networks, right? Even though, I mean, one would instinctively think that the sequential training would take much longer. Would you agree?
Well, if the sequential training is also based on the image representation, it will take longer. But the thing is, in micro stage, we are dealing with the world coordinates, the trajectory point. So we don't have to deal with the images at all in micro stage, so it can be done very quickly.
Okay, wonderful, thank you. Okay, so if there are no questions, Mihee, yeah, you can continue.
Yeah. So let's see the experimental results. In this paper, we demonstrate our model on 3 data sets, but in this presentation, I will show you the results of 1 data set, new scenes data set. This is a public autonomous driving data set, and it has 1,000 scenes in Boston, USA, and Singapore. And it provides the corresponding HD semantic maps with 11 annotated classes, such as drivable area, lane, road segmentation, etc. This image below is one example of new scene dataset when the scene is represented as a binary map, the navigable or non-navigable space. As you can see here, the entire scene map is very large. So in our model, we use the local view of the semantic map. And each scene of the new scene dataset is annotated at every 0.5 seconds. In our model, following the problem formulation of the prior works, we observe 2 seconds, which are 4 frames, 4 steps, and predict 6 seconds, which are 12 frames, 12 steps of the future trajectories. To give you the idea of how the predictions are made in each of our model, I will first show you the qualitative results, and then let's check the quantitative results. As mentioned earlier, we assume 2 short-term goals in our experiment. In long-term goal CVA, the one final step of the future trajectory is predicted. And 2 short-term goals and 1 long-term goal are predicted in the short-term goallet. Finally, in micro stage, the full future trajectories, 12 steps are predicted. Here, the 2 prediction cases are provided. That is, 2 different latent factors are sampled in the latent distribution of the long-term goal CVA model, and those latent samples are fed to the decoder of the long-term goal CVA to generate 2 different long-term goal predictions. And the corresponding short-term goal predictions are followed. Let's first see the prediction number 1. On the local semantic map, the blue ground truth past trajectories and orange ground truth future trajectories are depicted. The ground truth short-term goals and long-term goal are marked with X, like this. The long-term goal, short-term goal position, first short-term goal, second short-term goal, and long-term goal position. The ground truth data points are marked with X. And in this local map, we also overlay the predicted long-term goal heat map. The cyan colored area represent the most likely area where the long-term goal might exist. So in this case, we precisely predicted the long-term goal position because this cyan area is aligned with the ground truth position. Given this long-term goal, the short-term goal predicts 2 waypoints, the first short-term goal and second short-term goal and the long-term goal. We can see the first short-term goal area is well aligned with the ground truth short-term goals and same as well in the second short-term goal and the long-term goal. We can say that based on the past trajectories, which are slightly heading for the bottom direction, the future direction is most likely toward the bottom of the map, like this prediction 1 case. However, the agent may suddenly change its direction to the upper side of the map or go straight to the right side of the map in another instance, maybe. This is why we generate multiple predictions to compare the model ability. In the prediction of number 2, the long-term goal heat map predictions shows the possible long-term goal positions here at this cyan area at these 2 locations. But we can see the stronger cyan area is here at the top of the map. So this long-term goal position is fed to the short-term goal net, and the first short-term goal and the second short-term goals are generated so that the agent is heading to the top of the map. Technically, this prediction number 2 case is incorrect prediction in this specific instance if the ground truth is given like this. However, by having a model that can make these various reasonable predictions, we will be able to give correct prediction in another example. And finally, in microstage, I depict 10 different generation cases of full trajectories. The red dashed line is the predicted future trajectories. We can observe that most of these 10 different generations are heading to the bottom of the map, reflecting the past trajectory pattern, while getting enough diversity of the predictions like this way or that way. This is another example of the Newsyn dataset. The prediction number 1 has the long-term goal prediction here after the corner. So the short-term goal predictions are obtained accordingly. First and second short-term goal and the long-term goal. And in the prediction number 2, the most distinct heat map color is found here, though there is some cyan color here. So the short-term goal predictions obtained accordingly to this direction. And in these 10 generations of the complete trajectories in microstage, we can also check that most of the generations are achieved to turn the corner in the consideration of the past trajectories that showed intention of turning the corner. Here are the complete trajectory predictions of our model and the baseline models given the same instance. We can observe that predictions of trajectory plus and agent former tend to lead to collisions with environment. On the other hand, predictions of ynet and our model MuseVA are well aligned with environment, so it can be collision free. This is because trajectory plus and agent former, even though they encode the map, they encode the semantic map into one-dimensional feature, which entangles the spatial signals, while our model and ynet process the semantic map along with the trajectory heat map in 2 dimensions. So we use the UNet to process these 2-dimensional input and output the 2-dimensional images. Although ynet produces predictions that avoid collisions with environmental obstacles, ynet makes predictions with diverse durations. So it often overshoots the true future trajectory horizon like this. This is because ynet provides all the predictions in the pixel coordinate only using the heat map representation without understanding of sequential signal from the past trajectory, particularly the velocity, because they do not utilize networks effective to sequence learning, such as LSTM. On the other hand, our model, MuseVA's predictions are not only well aligned with the environment, but also reflect the learned dependency on the past trajectories because it's modeled by RNN in the micro stage. Now let's check the quantitative results compared to the baseline models. Let me first introduce several metrics to evaluate the performance. ADE, the average displacement error, is the L2 distance between the ground truth and predicted future trajectories, which is averaged over all future timestamps. And final displacement error, FDE, is the L2 distance between the ground truth and predicted final future step. KDE and then kernel density estimate based negative log likelihood value is to determine if the generative model can provide the output distribution that learns the characteristics such as variance and multimodality of the real future trajectory distribution. All of these three metrics, lower value indicates better performance. Lower is better. These metrics can be considered to evaluate the accuracy of the prediction compared to the ground truth steps, but we'd like to check how well the predictions are made, not violating the environmental constraints. So we use ECFL, environment collision-free likelihood. It is the probability that an agent has a path that is free of collisions with environment. So ECFL is obtained like this here. At the position PIT, where I represent the agent index, T denotes the time. EPIT is 1 if the position, if a PIT 0, PIT 1, PIT, the X position of PIT, Y position of PIT is located on the navigable space, then E of this PIT value is 1 and 0 otherwise. So 100 means 100 ECF value means there is no collisions at all with the environment. And in this table, we report these metrics evaluations. Following the prior works, we generate 5 or 10 predictions and report the best performance across these 5 or 10 predictions. In other words, we check the minimum AD, FD, KD, NNL across 5 predictions or across 10 predictions. And we get the maximum ECFLs across five or 10 predictions. And in this table, we can observe that in all metrics, our model can outperform the baseline models. And finally, I will show the results for the agent-to-agent confluction. Unlike the Y-nets, we have the last stage, the micro stage, based on the backbone of RNN. And so we can plug the pooling and collision loss strategy into this micro stage. In this table, we show the number of collisions between agents, our model, below each of the different thresholds in meter. So from 0.5 meter to 2.5 meter. In the ground truth new scene test set, there is no collisions at all at every threshold. But in the prediction, when we check the 5 predictions and get the minimum collision number, comparing our model with or without pooling and collision strategy, there are much more collisions between agents at every threshold when pooling and collisions are not applied. So by applying this strategy, we could reduce the number of collisions between agents. Let's see these qualitative results of one example. Here, each different color represent different agents' movement. The dashed line here, dashed lines, is the ground truth past and the future trajectories. And the dotted line is the predicted future trajectories. In this very crowded scenario, with pooling and collision model can predict the set of future trajectories without collisions between agents. However, in the without pooling and collision loss model, especially in this green agent area, this green agent is overtaking the other vehicles, red and blue agents, while making collisions with them, right? Like this, there is collisions. Also in this different example, without pooling and collision loss model shows conflictions between blue and red agents. See here, this dotted line predictions is overlapped at the same time step at this point. So we see all the experimental results. In conclusion, the Muse VA is a probabilistic model that can recognize the environment and generate multimodal predictions based on the coarse to fine approach. The macro stage, first stage, helps to reduce the uncertainty of the goal positions based on the understanding of the environment in pixel space. And then the micro stage can effectively learn the sequential properties of the trajectories while avoiding collisions between agents. Thank you for listening to my presentation, and please feel free for any questions.
Okay, Mihee, thank you very much. That was a very nicely developed presentation. So yeah, let's see. So any questions from the class? Okay, so Mihee, maybe one more quick question from me. So yeah, in relation to what I asked earlier, right, regarding specific improvements, and you sort of talked about some of the issues with the macro stage. So do you believe that the fidelity of predictions at the micro stage are extremely accurate, or like, can you speak a little bit about that? Can you speak a little bit about what you believe is the current prediction results at the micro stage, how dependent they are on the macro stage, and what you might do to further improve the micro stage predictions?
Yeah, micro stage is macro stage in micro stage is macro stage with two reasons. First one is to avoid the collisions with the environment. And secondly, because in the macro stage, the goal prediction, the uncertainty of the goal predictions can be reduced by the understanding of the environment. So without macro stage, with just micro stage, we will lose pretty amounts of accuracy, as well as we will have more collisions to the environment. And actually, if I have only the micro stage without the macro stage, that model is like the trajectory plus, because trajectory plus is based on the conditional VAE, and it processes all the sequence of trajectories based on the LSTM. And you can see here, there is significant performance difference. So I think macro stage is very important.
Okay, wonderful. And so maybe my one last question for you, and this is for the benefit of the class. So Sam, in his lecture last week, he talked about transformer architectures. So can you speak a little bit about how recent advancements in transformer-based architectures, right, might potentially be used for this particular task?
Right. Actually, that was the one I wanted to check if I have a time. So I wanted to replace this LSTM or GRU in my microstate to the transformer model, because usually people say transformer is more effective for sequential learning. Yeah.
Okay. But yeah, can you, and maybe you don't, because of course you haven't tried this, right? But can you maybe, provide some insights, right, on why transformer-based architectures might be more effective?
Because you will not lose the information of the long before the transformer does not suffer from the long-term dependency problem. So as the prediction of the future step is processed, the previous memories, like the very first future step information, is lost in the LSTM. But agent former, which use the transformer deals with the sequence of the trajectory at the same time by using the attention approach. So maybe that is more effective in terms of not forgetting the past information.
Okay, that's great. I think that's exactly what I was thinking as well. And from a practical standpoint, right? Like, since the training of transformer style architectures can be parallelized, right? So I guess it's much faster and easier to train, right?
Right. Yeah.
Okay, wonderful. Sounds good. So if there are no further questions from the class, right, everyone, please, let's thank Mihee for her great presentation. And as Mihee said, this work was recently accepted at CVPR 2022. So let's congratulate her on her fine work. So Mihee, thanks a lot.
Thank you.
All right. Okay, wonderful. So yeah, Mihee, we will now sort of switch over and talk about class-related things. So feel free to drop off the call.
Yeah, thank you. Thank you all. Bye.
Okay, wonderful. So let's take a quick 1 minute or 1 or 2 minute break. Okay, and then we can switch over to class to project updates. Okay, so I'll be back in about a couple of minutes. All right. Okay. So let's get the ball rolling so we can also try and end efficiently. So yeah, just to note on Mihi's presentation today, right? So hopefully you all found it interesting. So I think the the reason why I asked Mihi to present it, because this particular presentation is an example of an extremely structured and focused presentation, right, of a single publication or project, right, which was recently published. So I think it's a very good benchmark for you all as you all work on finalizing your respective projects and work on developing your final presentations, right, which are due in 2 weeks. So of course, I wouldn't expect, right, it would be uh, at the same level of depth as Mihi's presentation, which was nearly 1 hour long, and you all would have much lesser time. But definitely use it as a reference point. Okay, so that's just a note for you all. So any questions? Any other questions before we dive into project updates? Okay, so I don't think there are any questions. Yes, in that case, let's jump in. So let me just get my uh, uh, okay. So just give me a second. Okay, so yeah, let's start with the first team, right, which is the counter training object detection. So yeah, please feel free to share your screen if you all are present.
Uh, Professor, is the group one presenting right now?
Correct.
Okay, let me share my screen and about that.
Yeah, and before you get started, before you get started, right, at this point, of course, we you all have been giving these presentations on a weekly basis, so I don't expect, like, let's keep it quick and breezy, right? Okay, so talk about
Yeah,
your
understood. Yeah, I'll make it quick. So this week, as per our discussion and report, we need to switch to a new data set because the previous data set isn't very accurate. So we did some investigation, do some research based on the citation index. We find some data sets candidates are pretty famous and common. And among those data set, by considering this simplicity, we choose the Berkeley BDD 100K as the dataset to investigate, and then we make a script to convert their annotations to YOLO formats, and then we sample 1% of those data and manually review to see if they're accurate. So as you can see in those images with bounding box, they annotated very tiny objects. So and also based on our manual reviews, all of them are accurate. I don't see any results are missed clearly. So we suppose this one is a good data set to proceed. Compared to the previous data set, the small objects were ignored in the previous data set. This is not a good here because those will be captured as false localization if they're missed. So after reprocessing, then we use the we separate them into different sets, and then we use the training sets to retrain the YOLO model. And here's the performance, precision record at F1. And notably, it reached about 60% of accuracy and about 0.4 in the F1 score. And we use that retrained model to gather false predictions. And those are typical false localizations. They are such as some billboards are false detected as a traffic size, and the transformer box are mistakenly detected as a traffic lights. This is not, and also some dark poles are detected as person, and these are clearly false predictions. And then we use the false predictions to conduct error-driven learning. As you can see, it can boost the overall performance, but some problems still remains for the current error-driven learning. The performance will drop from the beginnings, and also it's kind of not very stable, as you can see some sharp drop in the process. And yeah, that's the progress in the arrow-driven learning. And thirdly, we also implemented the prototype network for automatically generated false predictions, because the false prediction annotations that we had relies on the ground truth annotation. We kind of want to automate this process so that we use the prototype network, and it's kind of a future classification networks. And here's the training in 5 short 20 weeks, and then we, after training, we perform the neural network to classify. Simply, we just add a few supported images and to form the cluster, the prototype, and then we use, based on the prototype, we input it all. We randomly sample a certain even amount of samples of each class, and then including false localizations, and then we measure their distance to the nearest cluster, and then we plot those distance. As you can see in this images, those triangles are false localizations, and circles are true localization. And as you can see in those high distance zoom, those false localizations are more likely to be in this zoom, and in the low distance zoom, those are mostly true predictions. So I think this could be an indicator of we can use that to discriminate it if a prediction is true or not. And I think in the next week, we kind of need to combine the prototype net to combine the prototype work with the arrow-driven learning YOLO. And by doing that, we can automate the false prediction annotation gathering. And that's pretty much it.
Okay, sounds great. So I think I'm actually making notes, right? So y'all might hear me typing. So I'll provide my feedback directly on Canvas. Yeah, so great presentation. Appreciate the update. Let's switch to the next group.
Right, thank you, Professor.
Thank you, thanks a lot. Okay, so next group is door differentiation.
Yeah, I can give the update. I'm not going to share my screen. All the charts and the graphs are in the Discord if people want to look at them. But essentially what we've spent the week doing is, because we had to create a custom data set, we started out by splitting the data set between train, validation, and test. So in our training set, we now have about 10,000 images. And we actually deployed our custom YOLO v5 model and started training it. At a high level, we're seeing about a 50% test accuracy across all the different doors that we're trying to identify. So about half are being identified and half are, so about half of each type of door is being identified. In general, they're actually not being misidentified. For the most part, it's either able to identify that the door is there or is not. There's sort of two exceptions to that. Doors with handles and revolving doors are being identified more accurately than other types of doors. And we sort of have talked about the reasons why this might be. Part of it could be that in particular for doors with handles, we had a lot more of them in our data set. So it's possible that because there was more training data, it's better able to identify these types of doors. Revolving doors also look very different to other types of doors. So that's another possible reason for why the model is having an easier time with those than say automatic doors, which can also sort of look like sliding doors. It could also be a data quality issue. We did have to put everything together from scratch. So we're trying to figure out what we can do to sort of up the accuracy on our model going forward. But this week, we've sort of just spent the majority of our time trying to get it working and get something that we could show qualitatively. So yeah, we're going to spend the next week sort of refining and trying to figure out a game plan for improving the test accuracy.
Okay, wonderful, Catherine. Thank you. And I appreciate the detailed qualitative results on your report. Okay, yeah, feedback on Canvas. All right, let's move on. So next is the ECA group. Are you all there?
I'm here at least. So we're all doing individual portions. So I'll go over mine. So mine being with affect-driven dialogue. So the repository that I'm using with the data sets, I still have that. I've yet to test it because, well, the class file that I'm using with Go called Go Emotions for actually testing, like actually classifying the emotions. That's being set up now. That should be set up within the week. But I have to change the actual emotional chatting machine that I've been using because, sorry, I've been trying to set it up for the past like week or two, and it's been giving a lot of bugs whenever I've been doing it. So this week, my main focus is going to be looking at I have other repositories already. I'm just going to be looking at them and setting those up, and I'll be connecting it with Go Emotions this week to actually like have data be processed between the two.
Okay. Anything else?
Yeah, I'm also part of the ECA project working on my individual portion. So for the past few weeks, I've been still trying to modify the embodied conversational agent, the speech to effective gestures project to make each gesture represent a different emotion. I've been able to alter them slightly, but the differences aren't as pronounced. So I'm still working with that code trying to solve that. In the meantime, I have been able to implement an affect text to speech. And then after I do that, I'll combine the both and get the statistical study done as soon as possible.
Okay, that would be nice to see.
I did have a quick question. So our final presentation is in 2 weeks, and then we have the paper due on May 10th. Okay.
Yeah, yes, that is correct.
Okay, so should we have the vast majority, so should all of our research be done within 2 weeks?
That's a great question, right? So I don't expect that, right? Right. So I think it's and the reason that we've set it up right where your technical report is due at the very last possible minute, right? Like essentially at the last day of exams week, is that y'all can use that time, right, to also, of course, make progress and put the finishing touches on your project. So yeah, the final presentation will essentially be right a detailed description of your approach and results that y'all have as of that date. But I certainly hope and assume that it will not be your finished product and that y'all will have more to speak about in your final submission. Okay.
Wonderful. Thank you.
All right. Thank you. Okay. So is your other team member here? Okay. Looks like
So
he isn't.
He did
Yeah.
put all his updates in the Discord.
No problem. I'll take a look. All right. Sounds good. So yeah, in that case, let's move along. GeoPixels.
Hello. My project was on floodwater segmentation. The baseline model that I implemented was Mask RCNN, and let me share my screen. Yeah, the previous results of the baseline model is already in Discord. In the last week, I was trying to implement another model, which is called point rend, and it's I think it's one of the most improved models in the literature. And I implemented this and compare its results with the baseline. The average precision of the mask RCNN for water segmentation was 63, but after implementing the point rend model, the average precision of the water segmentation had a very good improvement and reaches to 73. So here are some qualitative results. As you can see, for some simple cases, the improvement was not very significant, but for some other images which has more objects, the improvement was very good, like this. And here are some other results. The model is still need more improvement. For example, for areas like here, we can train the model with more images to solve these problems. And here is another result. So my plan for next week is to add some images that I found in COCO dataset. It is annotated as a class of river or sea or other water-like classes to add my current dataset. And also I found another dataset which is which contains images like this to decrease the bias of the model to street level images. Yeah, that's it.
Okay, sounds great. No, the qualitative results are really great. All right, thank you so much. Let's move on. A graph catch query.
Yes, this is group 5 and I'm Huang Zhang.
Mhm.
So maybe I can share my screen. So this week we trained the SketchGNN toward one of our data set, the patent citation network. And so this here I have some pictures that is the prediction from the synthesis data set. So here the see for example here the orange indicates that it is an 8 stroke, and the blue indicates it's a node stroke, and the green indicates it's the label stroke. And so intuitively it really gets a quite good result, and it actually reflects in the test accuracy result, where the P matrix means the accuracy based for the pixel based accuracy, and the C metric is the stroke based accuracy, and it really gets a high accuracy. But I need to make a note that means this synthesis data set is quite easy for this network, and in this sense, I'm concerning about its generalization. So what I need to make a note is that later I need to introduce some more noise or some more variations to the synthesis data set and train it another path. And yes, I think that's all the result that this week, and the next week we will connect to the other two network which recognize the label and clustering the graphs to finalize this whole pipeline.
Okay, wonderful, thank you. Yeah, I think as you said, right, it does look like you might have overfit your data, right? Yes. So which is fine, which is a good first step. But yeah, now you want to think about how you can address the overfitting issue, right? So as you said, data augmentation, making the synthetic data a little bit more complicated might be a good approach. Okay.
Yes, thank you.
Great, thank you so much. Let's move along. Imitation learning. Is anybody here from the imitation learning group? Okay, does not look like it. Let's move along. Music-driven animation.
Hello, Professor.
Yeah.
Yeah, so we are almost done with the animation part thing. So we used particular keyframes, which will be constituting to the animation part. So since we want to animate the walk cycle, we are using only 15 keyframes, which will be constituting towards our own complete walk cycle. Now we are experimenting with the Python library, which is the pretty MIDI, which handles the MIDI object and creates the beat. So we are now trying to synchronize the beats and the animation part. So we are just trying to experiment with the number of intervals, and also we are also trying to implement different algorithms which are used to synchronize the two signals. So the walk signal, so the walking part and the beats part will be synchronized using those algorithms. So for this week, we'll be just try to come up with a particular algorithm which will be used to map these beats and the animation part. And also we will try to create a GIF which will have the audio in the background and plus the animation part.
Oh yeah, that would be great to see next week, hopefully. Yeah, and then also always good to, when you're presenting these qualitative results, right? Always good to have like baselines, right, for comparison, right? So showing the motion without any of your ideas and showing the motion with your ideas.
Okay.
All right, great. Thank you so much. Let's move on. One short story.
Yes. So this week we worked on, we are working on two different parts. One is the token generation, which generates the next particular object in the sequence. So there we are exploring some new ideas this time, including the Dolly 2, which is recently released, and also the diffusion-based learning. So we're trying to incorporate new experiments and learning new networks on that. So that is more of the experimental phase that we did this time with the token generation. And the second part is the image generation. So there we tried a new method called distance transform. So sorry. So this was suggested by Professor Ahmed Elgamal, which is also our mentor here. So that is used to find the distance between the edges of the object so that we can find a relative good position for the next object. So that is what we tried. So we got the result for that, but what we're struggling is how do we iterate over that image and find a good location? Because if we do that iteratively over all the pixels, then it will take a lot of time. So because we have n cross n original image and some m cross m new image. So that is going to be 4 loops basically. So that is one thing we need help with. And we have to explore more on that. The next thing we tried in the image generation part was trying to get rid of the bad clip art objects that we have in the dataset. So again, we try to use a pre-trained classifier, but it didn't give us a very good results because we had a domain gap, because the kind of objects that we are using are mostly line sketches, but the classifiers which are trained are mostly the either real world or clip art based objects. So we didn't get a very good accuracy with that. We also tried to use a line-based classifier, but they were limited to very few classes, like 10 or 20 classes, whereas we have close to 300 classes in our data set. So for this part, we are planning to use few objects that inherently have good kind of drawings like basic objects like apple, clock, or these kinds of objects. So for now, we'll use those simple objects and move forward with that. Yes, that is the progress so far.
Okay, wonderful. Thank you. All right, let's move along. Sorry, just give me 1 second. Okay, sorry about that. All right. Next group, pyramid GAN person image. Yeah, can you please? Are you there?
Yeah. Can you hear me, Professor? Hello.
Yes. Yes, please go ahead.
Okay.
If you're speaking, I think you're a bit muffled. Hello, can you speak up? Hello, can you speak up?
Hello,
Okay.
Professor.
Yes.
Can you hear me?
Now I can hear you.
Okay. Oh, my work is still on the transforming from one pose to another. And similar to the object detection task, our task still has the network combined of backbone, neck, and the head. And my former work is mostly concentrating on the improvement of the neck. But having learned the transformer in last week shared by Sam, I also introduced the transformer to my work. I introduced the structure to the head to partly solve the problem of perception limitation of the convolutional layer. So I add the structure to the head, which means it is the image fusion block that fills the image feature and the close relationship to generate a new image. So I have posted the result on the Discord, and we can to quantize analyze. We can see that there's an improvement on I score, but there is a significant drop on SSM, which seems if acceptable. But if we look into the picture that they generated, the network without transformer can generate better result. Here, I guess there's two reasons. Firstly, as we know, as is known to all, transformer tend to need more data. So to solve this problem, we may use some techniques such as data augmentation. And another guess is that have add the structure to a wrong place. So in the next step, I can refer to the transcan on NIPS 2021 paper. So I can slightly change the place to add. Maybe it can work. But here we can witness that even if the S score is high in the work, but the quality of the image is not very good. So that's why we in this tag we mainly pay attention to the SSM score, the structural similarity. So in the final paper, I may further illustrate why we should drop the S score as a criteria. That's all. Thanks.
Okay, thank you very much.
Thank you, Professor. Right.
Yeah. Okay, let's go to the next group. Speech to image.
Hello.
Yeah.
Yeah. Hi. So for this week, what we've tried to do is we had last week generated landmarks out of the CNN and GRU model, and we have based on those landmarks, we've tried to train our DC GAN model. Not train, come up with an architecture. So what we have done is we have changed a little bit of the architecture in the DC GAN model, and we have changed things like the optimization used, or instead of using ReLU, we've used leaky ReLU and stuff like that. So the main problem that we were facing was coming up with an architecture that was best suited, because we were getting not great results at first, but eventually we did some research, and based on some of the papers and the parameters that they had used, we finalized a few parameters, and after a bit of experimentation, we've finally done, I mean, we think we've done a decent job, and we tested it on a small subset of the data, and it was like giving us decent results. So now we've already kept it for training, and we hope to achieve like good images by the end of this week, and hopefully complete the project as well. So that's where we are at. We've also uploaded pictures of our architecture and the landmarks that we generated, the sample landmarks, on Discord. So if you guys want, you can go have a look there as well. I guess that's all.
Okay, thanks. Thanks a lot. Just a note, as you're exploring different architectures or different hyperparameters, right? A little bit more informed approach to doing that, right? Doing some kind of hyperparameter search. I mean, I understand looking at other comparable works and borrowing from that is a good approach, but a little bit more grounding on how you choose, how you make those choices would be appreciated. Okay, but otherwise good. Thanks.
Thank you.
Okay, the star team. The star semantic team, are you here? Okay, let's move along. Virtual try-on.
Yeah, hi, Professor. Hello.
Yes, please go ahead.
Yeah, hi. So, so last week we were finalizing the APIs for segmentation and open pools. So we were able to complete that, and this week we mainly focused on creating a script for integrating different parts of the project. So we created a script for which basically takes input person's image and input load, and calls the segmentation and open pools APIs, and feed it to the v.ht model, and gives us the result. So we have like the pipeline ready. So now for this week, we will be focusing on creating like integrating it with the application web app. So like in terms of qualitative and quantitative results, we still have the previous week's results, which are pretty good. But like we are right now focusing on images as of now, because the average response time we are getting is approximately 10 seconds, 10 to 12 seconds. So once we have the app ready, so we'll then focus on try to improve the performance so that we can actually use it for live videos.
Okay, wonderful. So do you believe y'all will have an interactive app perhaps ready for the final presentation?
Yeah, that's right.
Okay, that would be great. All right. Sorry, taking some notes. Okay. Let's move along. VR space design.
Hi, Professor. This week, what I accomplished was I added to the environment of the VR scene. To use this, I continue to use the package I already have, and then pulled some more stuff from the Unity Asset Store. Essentially, the goal here was to create it so that it looks like a town, and so that participants know what's, they feel like they're in an actual town environment. So I had to make it like a cohesive scene where each of the spaces were flowed into the next one. And then to that effect, I also had it where I added in additional sounds. So before it was just ambient wind noise. So I also added crowd noise for the spaces that had more than one NPC. And then I also added in so that the NPCs would randomly cough if the participant was nearby, this way to see what effect that would have on their behavior. And then all the sound was done with 3D spatial audio. So it falls off as you get further away, and it also will change depending on if you're looking at it from behind or with one ear closer to than the other. Additionally, the other thing I mainly worked on was there were some bugs that came up with the Oculus Quest that Serena was using, my mentor, so I had to help fix that a bit. And then I also found some bugs with the HTC Vive that I was using. And so I had to fix that so that I could render without issues and lag on my end. Outside of that, the main focus I'm going to have is working on Q&Aing it myself, and then I'm going to share the APK with Serena to QA with her, and then I'm going to also try to see if I can QA with other people that I know, like friends and so on, just to make sure it works. And then this week, I'm also going to try and make it so that the spaces are more procedurally generated. So right now it's fairly linear. Like if you do it once, you know exactly what's going on. So my goal is to like swap it out so participants, when they retry it with both scenarios, don't automatically know what's going on to get more of an actual like proper response. Yeah, that's the main things.
Okay, wonderful. Is there a timeline for initial experiments, like a pilot study?
I need to speak with Serena about that, but I was hoping to QA it this week and then maybe start next week, but I'll check with her.
Okay, wonderful. Sounds good. Thank you so much.
Yep.
All right. I think that brings us, right? I believe, yeah, we went through the updates very quickly. So maybe some students or some teams, right, that we might have missed. Is anybody there? Okay, I think looks like we went through, right? We got everyone. Oh, so Catherine has a question. Since the final presentations are on 4/25, do we have a lecture on 5/2, which is the last day of classes? I think the answer is no. Let me just double check. So I'm just reverting back to the. Sorry, just give me 1 second. Trying to find. Yeah, sorry, I can't seem to find my the Excel sheet where I have set up the class schedule. But yeah, I think yeah. So the final presentation is going to be the last day of classes, right? So if there is, so I believe, yeah, I think the way I set it up was right that the following Monday, which I assumed would be exam week, right? There would be no class on that day. Okay. All right. Any other questions? Any other questions?
Excuse me, Professor.
Yes.
I have a question about the qualitative results of my work. I'm still confused about what the qualitative results of my work, to generate perfect image in my test. What can be the qualitative results?
Yeah, that's a good question, right? I think in some of my feedback to a few of the groups, right, I had requested, right, that you all provide more detailed results, right, either qualitative or quantitative, right? Yeah, so I think so with respect to your group, so you and I, we can have an offline conversation, right, about how you can perhaps present some more detailed results. Okay, but yeah, we can talk about that on this call.
Okay, thank you, Professor.
Okay, no problem.
Sure.
Any other questions? Just a note, I believe all the groups are doing pretty well, right, in terms of grades. But if any group wishes or would like, right, to improve any of their past grades, please reach out. Okay, again, as I said, I'm here to give you all every opportunity, right? And eventually the culmination of this class, right, which will be your final presentation and your final report, right? That will, will essentially heavily influence, right, your grade. But yeah, if anybody would like to improve some of their past assignment grades, reach out to me and we can discuss a strategy, right, of additional results or some additional descriptions that you all can provide to help improve any past assignment scores. Any other questions? Okay, looks like there are no further questions. All right, so in that case, I think we can conclude a little bit earlier today. I'll stick around on Zoom for a few more minutes, right? While if there are any other questions for me. Otherwise, yeah, have a great week. We are nearing the end, and I think everyone's making wonderful projects, right? So excited to see your final presentations in a couple of weeks. All right, yeah, bye everyone.